All right, we'll now talk about section 1.2, which deals with graphs of quantitative data and also describing those graphs. Section 1.1 dealt if we had categorical data. So first of all, let's read this context here, and then we'll talk about what we need to be able to do in this section. It says the time that it takes workers at a factory to assemble a part to a boat motor on a particular day is shown below in minutes. So we're asked to create a dot plot with the data and a histogram. So the first thing to recognize is that this data is quantitative. It's numbers. And so quantitative data just deals when basically every individual has a number associated with that individual. So so that with people, that could be something like height or weight or time to do something, which in this case, that's what that'd be. Now, categorical data, which is what we did in section 1.1, is when it was categorizing the individuals, such as with people, like by their hair color or by their race or by their religion or what state they were born in, something like that. And the numbers involved in categorical data are just counts in categories, but this is definitely quantitative data. There's four main kinds of graphs you got to be able to do with quantitative data. You got to be able to do a dot plot and a histogram, which we're going to talk about here, and then also a stem and leaf plot, which we're going to do in a minute, and then a box plot, otherwise known as a box and whisker plot, which we're going to do in section 1.3. So, but the focus of this section, the goal for section 1.2, is to be able to do a dot plot, a histogram, and a stem plot, and then to be able to describe the distribution by using what we call cussing. And we'll talk about that in a second. So those are the main goals of this section. Be able to do a dot plot, be able to do a histogram, be able to do a stem plot, and to be able to describe the distribution using cussing. So that's what you really need to be able to do. So the first thing we'll do is make a dot plot. Now all a dot plot is, it's just a number line with dots above it. So you just make a number line, and so in this case you notice that the data is varying from 12.1 minutes to 32.7 minutes, and you just make a number line, make sure and scale it by putting numbers. Technically, if you just put two numbers down, you get credit for scaling, and make sure and label it by putting what it is. That's very important. You always label and scale your graphs. It doesn't have to be a perfect looking graph. You just have to, the whole goal of these graphs is to, in general, understand what's happening with the data. So if they're off a little bit, it's no big deal. And so we would look at this and we would actually, and I'll explain this momentarily, is we would say this data is skewed to the right. Its centered is somewhere, around 18, and it would be skewed to the right. In other words, it kind of has a tail going to the right. But that's how you make a dot plot, and so that's the first kind of graph that you need to be able to do. And some of these graphs can get a little complicated, but look, if you get confused about something, just make a dot plot, number line with dots above it. All right, so the second thing we're going to do is we're going to make what is known as a histogram, and which is probably our most complicated graph. And to make a histogram, the first thing we have to make is what is known as a frequency table, and frequency tables have frequently been on the AP Stats exam. To make a frequency table, to make our histogram, we've got to create what is known as classes, or in essence intervals of numbers. We are going to categorize these numbers. And what we'll do is we recognize that these numbers are going from 12.1 to 32.7. So I'll go ahead and start my classes. I want to capture all the data. So I'll start up my classes at 12. That'd be a good place to start. Now I want to have at least like 4 or 5 classes certainly. So how big should I make my classes? You could say, well, if I made the class sizes of 5, then I would have 4 or 5 classes, but I'm going to make my class sizes 3, and so the first class will go from 12 to 15. Now you've got some liberty there, so when people make different frequency tables with the same data, they can look different, and their histograms can look a little different, and that's okay. So depending on your class sizes, but anyway, so I'll just pick class sizes of 3, and so start out with 12, and so the next class goes from 15 to 18, like that, also a size 3. And you may say, well, which class does 15 go with? 15 goes with this class. All these classes are inclusive on the left side, so 12 goes in that class, 15 goes in that class. So this is all the numbers from 12 to 15, but not including 15. This is all the numbers from 15 to 18, but not including 18. So every number up to 18, 17.999 would go in this class, but 18 would go in the next class. And so the next class, 18 to 21, and then the next one, 21 to 24, and then 24 to 27. And I keep making classes until I capture all of the data, which will go to 32.7. So there we go. And so we've got ourselves 7 classes, and that's a good number of classes. Now what we'll do is we're going to create tally marks that we call frequency. And it certainly helps that this data has been put in order. So I just tally for all the numbers between 12 and 15. So 12.1, that would go there. 12.3 goes there. 14.2 goes there. 14.9 goes there. And then 15 would go in the next class, like that. So there's 4 in the first class. And so how many are, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 numbers that are between 15 and 18. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then between 18 and 21, we've got 1, 2, 3. So 1, 2, 3. Between 21 and 24 is just 1. And then between 24 and 27, we've got 1, 2. So we've got 2 in that class. And then between 27 and 30, we've got 1. And between 30 and 33, we've got 1. There we go. And so there is our frequency table. That's how you make a frequency table. And so to make a histogram, we're going to graph the frequencies. It's in essence kind of turning this frequency table sideways. So what we do is this. So to make a histogram, this would be a histogram. Looks like a bar graph, but it's not a bar graph. Don't get the two confused. Histogram is with quantitative data. Bar graph, like we did last section, is with categorical data. So our frequencies go up to 9. So on a histogram, your y-axis is going to be frequency, or it could be relative frequency, as we'll talk about in a second. But so we'll go up to 9. And so we'll go 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 1 to 9, and 3, 5, 7, let's say. And then you just put your classes on your horizontal axis. So those will go from 12 to 15 to 18 and so forth. And then what you do is you just put bars going up to your frequency. So between 12 and 15 is 4. Okay? And that includes 12, but it doesn't include 15. All these bars included everything below that. So the next one goes up to 9. So that's between 15 and 18. And the next one goes up to 3. So 3. So it's like there. And then the next one's 1. And the next one between 24 and 27 is 2. And then the next 2 are both 1. So it goes like that. There you go. And that's how you make it. Now, make sure I've scaled it. Make sure and label your what you're doing here. And so the label is assembly times. So the label is assembly times, and always put your units. It's in minutes. So there we go. And that's how you do a histogram. Notice there's no gaps between the bars. The only way there's a gap between the bars is if one of your classes had 0 in it. Then you'd leave a gap. And that's the difference between this and a bar graph. On a bar graph, you would leave gaps between your categories. In a histogram, you don't. But don't call this a bar graph. It's a histogram. It's with quantitative data. So there we go. All right. And so the next thing we want to do, that I believe we're going to be asked, is to describe the histogram by using cussing and then describing its clusters and gaps. And so this is what we mean by cussing. Whenever you're asked to describe a distribution is just a list of numbers. Whenever you're asked to describe it, you have to cuss. And so to cuss, the C stands for you must describe its center. Where is it centered at? Now, and in the next section, we're going to have numbers to describe the center, the mean and median. All right, then the U is unusual values. Does it have any unusual values that we call outliers? And we'll have a formula in the next section that will define outliers. Then it's shape. And we'll talk about, is it unimodal? Is it skew to the right, skew to the left? We'll talk about that in a second. And lastly, it's spread. Okay, how spread out are the numbers? What's the variability? And we're going to have some statistics that describe spread, namely the standard deviation, the interquartile range, and the range. And we'll talk about that in the next section. And in regards to, is there any clusters or gaps of values? All right. So let's do that very thing. So let's do that very thing with this distribution. So with this distribution, this is, all right, first of all, what's the center? And in the next section, like I said, we're going to come up with a couple numbers to describe center, and the mean and the median. But it's just, what does the middle appear to be? Well, it's around 20 or so. So you would write the sentence and you would say, well, the center is around 20. And then, are there any unusual values? Well, when you look at this, there are 32.7 and 29.3. They're kind of way out there. They're a little unusual, so they might be outliers. And like I said, we'll definitively define them in the next section. But outliers are just unusual values relative to the pattern of the other values. Then in regards to the shape, this is what we're going to call skewed to the right. Skewed to the right means it has a tail going to the right, and it's going to pull its mean bigger than its median. But that would be skewed to the right. And then lastly, it's spread. You could just say, well, the numbers vary from 12.1 to 32.7. So let me show you that paragraph. So in regards to this data set, this is the paragraph that I would write if I was asked to describe a distribution. So as to describe a distribution, I have to cuss. And I would just say the distribution of assembly times, always mention the context, by the way, is centered around 20 minutes or so. So that would take care of the center. There may be outliers at 29.3 minutes and 32.5 minutes. So that's the unusual values or outliers. The shape is skewed to the right. And then lastly, the assembly times vary from 12.1 32.7, so that describes the spread. All right, let's talk about this. Let's talk about what do you have to do in describing the shape, and that's going to take a little bit of practice. But here's some terminology that you can use that you need to be aware of in regards to shape. In regards to describing the shape. First of all, it could be symmetric. Symmetric means is that the right half of it looks roughly like the left half. It doesn't have to be exactly symmetric, like mathematically symmetric exactly, but as long as it's close. So if we have a histogram like this, let's say we kind of rounded off the little boxes of the histogram, and it looks like that, we could look at that and we'd say, well, the right side looks roughly like the left. If you were to cut it in half, it's kind of the mirror image. So you could describe that shape as symmetric. And it's also unimodal. You know, modes are wherever it sticks up. And so like this histogram, which we just did, it's unimodal. Mode is a place where it's just sticking up like that. Technically, the definition of the mode is the number that occurs most often, but for us, it's just any place that sticks up. And this looks pretty unimodal, I would say. But it could be bimodal. All right, bimodal would be something like this. Let's say it has a place that sticks up there, and then it has another place that sort of sticks up, maybe even not quite as high. So we would look at that, and we'd say, hey, that's distinctly bimodal. It has two places where it sticks up. Now, left skewed means this. Left skewed means it has a tail going to the left. It has a tail going to the left. So it looks like this. So it looks like that. Let's say. That would be what we call left skewed. And in the next section, we're going to talk about the reason we call it left skewed is because it's going to pull the mean to the left. Right skewed is the opposite of that. It has a tail going to the right, so a tail going to the right. And so it's going to look like this. It's going to have a big thing there, and it's going to tail off like that, like the distribution we just drew with that histogram. So that would be distinctly right skewed. Or another term that you could use is uniform. Uniform means just roughly it's going straight across. All the numbers are occurring pretty much the same. So it looks almost like a rectangle. We would call that uniform. So uniform is straight across. And so, of course, later in the year after chapter 2, we're going to talk about approximate normal. This data looks right here. This looks approximate normal. But those are the terms you really need to be able to say in regards to describing shape. And so that, like I said, that takes a little bit of practice. You know, and the center is pretty straightforward. You're pretty much going to state its mean and median. And the spread is pretty straightforward. You're going to pretty much state its standard deviation, IQR, and range. And like I said, we're going to talk about all those numbers in the next section. But shape is a little ambiguous. And outliers, we're going to have a formula that picks out outliers, and so that's kind of straightforward. Shape is a little bit subjective. So anyway, and so that is really the heart of the section, being able to cuss and being able to do a histogram dot plot. Now, let's say this. Let's say you were given two distributions, in other words, two lists of numbers, and you were asked to compare the distributions. The key thing is whenever you're asked to compare distributions is to cuss using comparative phrases, like it says here. Now what that means is this. Let's say if there was two factories, not just one. And so you had, well, this is factory 1, and here's the amount of time it takes them, factory 1. And let's say you're given another factory. This happens a lot in the AP exam where they give you two lists of numbers. And this factory's times are this, 14.7, comma, dot, dot, dot. And they give you another list of numbers. And they ask you to compare them. So what you would do is you would cuss using comparative phrases. In other words, you would say, well, the center of factory 1 is around 20, which is greater than the center of factory 2, which was around, let's say, 18.5, or whatever its center is. You know, or maybe it's like, let's say it's measures of spread. You could say, well, factory 1, it varies, you know, from 12.1 to 32.7, and so that means its range, which is the biggest minus the smallest, would be 20.6, is less than the range for factory 2, which let's pretend was like, you know, 25 or something. Okay, and then you would describe both of their both of their shapes and whether or not they had outliers. But the key thing to remember is to use comparative phrases, is to cuss using comparative phrases. And let me demonstrate that with another problem. So let's demonstrate comparative cussing. And we're also going to make the other main thing in this section is to be able to make a stem and leaf plot. And so that's the other main type of graph, or what we call a stem plot. So you notice in this data set, it is quantitative data, lists of numbers, and there's two lists. And so you say, hey, we may do some comparative cussing here. But let's look and see what we have going on. So it says there are two locations of a restaurant in a city, one near a river and one located downtown. At each location, the amount of money in hundreds of dollars, so that's something that you pay attention to, what our units are. They're in hundreds of dollars. So doesn't represent 22, that represents 2,200. Okay, well anyway, earned on a number of randomly selected days, and that's going to be a really important thing for us later in the year, the fact that we've randomly selected these days. And that basically means is that every day was equally likely to be chosen. That's what random means to us. And so we're going to create what is known as a back-to-back stem plot and compare the distributions. All right, so this is what we're going to do. First of all, I'm going to just take the downtown. I just want to make a regular stem plot first, and then I'm going to make a back-to-back one. So, and I'll just do it with, let's say, with the downtown numbers. So, and you may have done this in years past to make a stem and leaf plot. So, this is what you do. So, your stem, you want to pick your stem to be the number that occurs on the left side. And so, our stem in this case, all of them. Or in essence, two-digit numbers that have a number in the tens place and the ones place. So I picked the tens place to be my stem. Now, in actuality, that's going to be like the thousandths place. But anyway, and so you notice these set up nicely for a stem and leaf plot. And so the numbers, and I'm going to go ahead and start with 2, since my other one starts with 2, by the way. So this will be 2, 3, 4, 5, and 6. And so that represents the tens place of these numbers. Now my leaves, I go like this. So stem, here's leaf. And so what I will do is 37, I put a 7 there, represent the ones place. So the leaves represent the ones place. And so this is just a way of graphing the data in essence. And so then I go 42, and so I put a 42 like that. And then 46, 47. So I put that for a 46 and that for a 47. And then I've got 49, 49 like that. And by the way, it's critical that my digits are the same width. Like I go to 51 now, it wouldn't be correct in essence to go like 51, 52, 54, because look how bunched in they are. All the digits need to take up the same width in order for me to properly see the shape of the distribution. So this is 51, 52, 54, 54, and then 56, 58, and 59, and then lastly 60 goes there. And the last thing that I need to do is to put a key that tells the reader of this thing what these digits represent, and realizing that 3/7, 3, this is in hundreds of dollars, so that represents 3,700. That represents $3,700. And so that's telling the reader, the key tells the reader of this thing that the stems represent the thousandths place, and then the leaves represents the hundredths place. That's how you make a stem and leaf plot. Now, of course, we always have to label it. This is the, this is the downtown. So our leaves are the downtown, is the downtown money, the downtown. And so so I've properly labeled it. Now, that's how you make a stem and leaf plot. And if you're asked to describe that, you would say, well, I would cuss. The center of this thing is, somewhere around 50, I would say. The shape is pretty symmetrical, mound-shaped, as we could say, or unimodal. And in regards, there appears to be no outliers, no unusual values. And in regards to the spread, the numbers vary from, 37 to 60. And so the range is going to be 23, as we will discuss next time. So that is a stem plot. But we're going to make a back-to-back stem plot. Okay, back-to-back means we've got another data set. So I'll graph the river location over here. So I'll put the stems in the middle. So over here, I'm going to put the river leaves. And so I'll do a similar thing over here. And so 22, 28. So I've got, 22, 28. So like that represents, so you read it from right to left on the left side there. So this is 35, 38, so 35, 38. And then, 44, 48, 49, 44, 48, and 49. And then 53, 58, 53, 58. And then 61, 66, 61, 66, 68. And it's got some 70, so I have to extend it. So 72, 79, and of course the same key applies, so that's good. And so there we go. That's how you do a back-to-back stem plot. So let's say if you were asked to describe the distribution and to compare. It says to compare the distributions. So what you would do is you would write a paragraph really similar to what that paragraph we wrote before, really similar to this paragraph that we talked about, except we're going to do comparative cussing now. So we would compare their centers. So compare their centers using comparative phrases. And they're both centered about the same thing. You'd say they're both centered somewhere around 50. So you would say the center amount of money for both the river and the downtown restaurant is roughly about $5,000. So that would be comparing their center. Unusual values. Neither one of them has what appears to be an outlier. In other words, one that is just way out, away from the pattern of the others. I mean, you're always going to have sums on the ends, but outliers means it's sort of way away, and we'll have a formula to describe that in the next section. So you would basically say neither of them appears to have an outlier. And in regards to the shape, you just describe their shape. You would say, well, the shape for the downtown is, is pretty symmetric and mound-shaped, whereas for the river, I would say that's pretty uniform. It's going pretty much straight across is what I would say, the way I would describe that. And then lastly, the spread, you would just compare those. You would say, well, the spread for the river, the numbers vary from 22 to 79, and so its range is going to be 57, which we're really defining that in the next chapter, whereas for the downtown, the numbers vary from 37 to 60, and so its range is 23. And so this one has significantly more spread, the river location. And that's sort of the main thing you really sort of need to notice. And so shape and spread. And we'll, like I said, put more numbers on these in the next section. But the main thing you need to notice about this is you would say they're centered around the same thing, but the river has more variability. That's what really stands out. The downtown one are more consistent. They're more bunched together. All right, and then the last thing we're going to talk about in this section with the stem and leaf plot is that sometimes it may be best to do what is known as split the stems. All right, split the stems basically means is we're going to create more than one row here for each of our stems. And it's important that each row has the same number of numbers. So what we can do if we split our stems, if we can split our stems, we could say, I'll put 2 2s. And this represents, so the top one represents all the numbers between 20 and 24. It represents 5 digits. And then the second 2 represents all the numbers between 25 and 29, also 5 digits. And then I'll put 2 for 3s. So that represents every number between 30 and 34. And that represents every number between 35 and 39, and so forth. And if you did this with this data set, if you split the stems, here's what your back-to-back stem and leaf plot would do. So notice, you know, the top one, like for the 40s, this 40 has everything between 40 and 44, and this one has all the ones between 45 and 49. And that's true for all of these, okay? Now, what that does, it has you create more classes. So that's a technique that's used. It's important to note that each of these pairs has the same number of digits. So you really need to either do 2 classes with 5 digits in each, or you could do 5 classes with 2 in each if you had a large data set. But that's just a different view of it. It's still the same data, but it's just a different view of our shape, which I would still say the same thing. It's pretty uniform for the river, and it's pretty mound-shaped and symmetrical for downtown. All right, so that's it. But I encourage you to do, read section 1, 2. Look at those examples. That's the best way to learn statistics, is seeing things in a number of different contexts and apply it in a number of different ways, and see if you can do the homework problems and ask questions about it.